Good afternoon. So Dr. Nietzsche is away today, so I'll be running the lecture today. So we had the midterm on Monday. It has been graded. Scores have been posted. The key should be up sometime before the end of the week. I promise that it will be thorough with the calculations, which is why it's taking me a little longer to do it. The average was somewhere between 72 and 73. I think it was 72.4, which is a scotch over 60%. Which, hey, come on, it's not so bad. The average overall score for the three combined midterms, overall average score is around 70%. Which is good if you'll look at the grading rubric on B-Space. 70% is right at the C plus B minus border-ish area. So that's not so bad, especially considering, right, we get 100, we get lab points and homework points and free attendance points, which aren't nearly as difficult to obtain. So, you know, don't be all morose and everything like that. It'll be okay. So, no, I didn't write the test. I did not write the test. So, we have, of course, the one item of business to take care of, which is the midterm bonus question. So if we can all get our eye clickers out, and if we can all quiet down, no sharing with your neighbor, we can get started with this bonus question. So, the reaction between carbon tetrachloride and water, simmer down now. There we go. Reaction between carbon tetrachloride and water to form CO2 and HCl has a delta G value of negative 232 kilojoules per mole, and so it is thermodynamically favored. But when you mix carbon tetrachloride with water, no change is observed. Which of the following can best explain this? Let's get started. And if you were here this morning and clicked in this morning and you click in again in this afternoon, you don't get any points. So, you know. Okay, 244. Wow, that's a lot more than this morning. Okay, so let's look at the answer. So we've got four choices here. We can have a thermodynamically favored reaction that still does not occur, and the best way to explain this is B. It's a slow reaction kinetically. How'd we do? 100, all right. There we go, all right. So, let me get a new eye clicker section here, and we will get going. Where is that? There we go. Okay, so if we remember last time, we have been talking about equilibrium, and we started talking about different types of equilibrium, heterogeneous things, gas, right, and aqueous phase equilibrium like you have with carbon dioxide that we all know from our soda or carbonated waters. We talked about solubility products, that is how solids are going to dissolve into a solution, and talking about the equilibrium that way. We also did the little light bulb with the titration. That's always cool. But today, we're moving forward to another type of equilibrium, which is acid-base equilibrium. And this is one that's rather important for all of us because our body has a lot of these reactions that are going on all the time. And should we happen to change the pH in our body by more than about 0.1, we'll talk about pH later, then we would die. So we have a very specific pH, and most animals do, that you want to be at. You can't have this whole range. So we're going to talk about acid-base equilibrium, how we describe acid-base equilibriums in terms of the kinetics, or not the kinetics, in terms of the equilibrium that we've been discussing in class. So when we have acid-base equilibrium, there's a couple of different ways that you can talk about describing an acid. One of the first was by a physicist by the name of Arrhenius, who is one of the forefathers of physical chemistry. And when Arrhenius was talking about acids and bases, his description was acids are things which, when put in water, give off H+, and bases are things that, when put in water, give off OH-. And this was an okay description. And then in about 1927, 1930, there were two guys. One was an English scientist by the name of Lowry, and one was a Danish chemist from Copenhagen by the name of Brønsted, with the /O. And Brønsted and Lowry described acids around the same time as being proton donors and proton acceptors. Acids donate the proton, bases accept the proton. Now, one thing that you need to be aware of when you're listening to these lectures, when you talk about acids and bases, you can talk about H+, H3O+, or protons, and they all mean the same thing. Because if I have H+ in water, it can attach itself to a water to form H3O+, or you can talk about it as the proton, which is on your acid. And you can have several different protons on a compound, but when you're talking about one that is acidic, can also be referred to as the acidic proton. So, sort of talk about this, we get to go back to my basketball. And I'm from Indiana, so I love basketball. And whereas before we used the basketball to talk about electrons, now we're going to use the basketball to talk about protons. So if the basketball is my proton that's acidic, and I have it, what am I? I'm an acid, because I've got a proton that I can give away. So as soon as I give this proton away, that's being an acid, is giving up the proton. Anybody like basketball in here? Like basketball, a little few basketball fans? I need a hand. I need someone to help me. Yes, come on up. So, I've got the basketball, and if I am an acid, right, I want to give up this basketball. And you are a base over here, and you're like, hey, I can catch the basketball, so here you go. Now, I don't have the proton anymore. What am I now? I'm a base. And what are you? An acid, because you've got a proton that you can send back to me. And so we can have various strengths. Oh, we're not done yet. Oh, no. We can have various strengths of acid or base. If I'm a strong acid, then I really want to get rid of this ball, right? So every time I see a base, I'm going to give it the ball. If you're a strong base, then you want to catch it anytime it's available. Now, If I am a weak acid, right, I have a lot of acidic protons, but I don't give them up very easily. I'm like, you know what? We're thinking about it, and I can do this for a while, and eventually I'm going to not catch it, and it'll go away. But if I'm a weak acid, right, I keep a hold of most of my ones, but every now and then I'll give it up. Now, another way you can think about this. So, we got any Lakers fans in here? You know who the best team in basketball is? The Cavs. But that doesn't work well for my example. So who's the best player on the Lakers? Kobe. We want to score a basket at the end of the game to win. Who do we want to have the ball? Kobe. So you're Kobe Bryant, okay? I'm Jordan Farmar. I'm not very good at basketball compared to Kobe. So if I've got the ball with about 5 seconds left, I want to keep that ball, or do I want to give it to Kobe? We want to give it to Kobe. So we'll give Kobe the ball. So when it comes to that, I'm going to be a really strong acid. Because if I'm Jordan Farmar and I've got the ball and I see Kobe Bryant looking for it, I'm always giving Kobe the ball. But if Kobe's going to shoot, is he going to feed Jordan Farmar for the game-winning shot? Not so much. Not very likely. Kobe really wants the ball at the end, strong base. Now, maybe if like all 5 guys guarded Kobe and he was on one leg and not looking, then maybe he'd feed Farmar. So it can happen. But for all intents and purposes, not going to happen. So, thank you. But what we're getting after here is that when we have an acid-base equilibrium, right, I have my acid that wants to give up the proton. But once it gives up that proton, then it can act as a base. Because then it can, if we do the forward reaction here, I've got my acid with the proton. It gives up that proton. Well, if we go in the reverse direction, then this A- here can pick up a proton to reform the acid. And if it takes on the proton, by the Brunstad-Lowry definition, that would make it a base. So we would refer to this as HA as being the acid, and A- as being its conjugate base. Likewise, if I've got a base B that wants to accept the proton, it forms BH plus in the forward direction. But if we go in the reverse direction, it can give up at this to reform B to the base here. So again, we have a base and its conjugate acid. And so we can see that, because it's in equilibrium, we can go both ways. So we either have the acid or the conjugate base. So we can list several acids here. Water can act as an acid. We have acetic acid, or vinegar, also has the one acidic proton here. And H3O plus also can act as an acid, right? It can give off one of those protons. So what are the conjugate bases for these? Well, if H2O loses a proton acting as an acid, what does it become? OH minus. HAC loses a proton, it becomes the acetate negative. And if H3O plus loses a proton, it would become water. So here we go. We have the corresponding conjugate base for these acids. And so we can see that OH minus over here is going to be the best base because it comes from the weakest acid. H2O is the worst base because it comes from the strongest acid. Okay, again, because it's an equilibrium, it goes forward and backward. And if it's favored one way strongly, it will not be as favored to go the other way. We can also look at our bases. We can have water also. Again, we see it's an acid here. Now we're looking at water as the base. We can also have ammonia and OH minus. OH minus being the strongest, ammonia in the middle, and water being the weakest as a base. But when we look at the protonated form of the base, or its conjugate acid, OH minus becomes water, NH3 becomes NH4 plus, and water becomes H3O plus. Right? And we see up here, we know H3O plus is stronger than water as an acid, right? And same works as the conjugate acid. So we always have these pairs of acid, conjugate base, base, conjugate acid. So we saw that water works both as an acid as a base, so we can talk about the dissociation of an acid in water as an equilibrium thusly. We can have some acid here which will react with water to produce H3O plus and the base A minus, the conjugate base. And since water acts okay as a base, and if we have an aqueous solution, what does it mean to be aqueous? Dissolved in water. And so if we're dissolved in, if I'm an acid and I'm aqueous, that means I'm dissolved in water. So what can I usually find around me? Water. If I'm dissolved in water, there's a lot of water around. So we can talk about this equilibrium. And we can write an equilibrium constant for this expression, just like we've been doing before. So what's my equilibrium constant going to be? Concentration of products over reactants, right? So we would have concentration H3O plus, concentration A minus, divided by concentration HA. And we have this equilibrium constant right here. Where's water? Where are you going? Nowhere. Water's a liquid, so it's a pure phase, so it's not going to be in our equilibrium expression. And we call this equilibrium constant Ka, and the sub A indicates that it's an acid dissociation constant. And so this is another way we can get at the strength of an acid. Because if an acid is strong, what does that mean? Give up the rock. Get rid of the proton. So the stronger an acid, the more it wants to get rid of that proton. And so if an acid gets stronger, it wants to get rid of the proton more. So what's going to happen to this H3O plus concentration? In this expression, we would increase it, right? Relative to the concentration of HA. We're going to see more deprotonated, more of it giving up the proton than staying protonated the stronger it gets. So a large K value means a strong acid, and a small K value means a weak acid. And the general rule of thumb is if Ka is greater than 1, it's going to be a strong acid, and if Ka is less than 1, it's going to be a weak acid. And there's usually a several order of magnitude disparity between the two. So strong acids would be things like HCl, HBr, HI, HNO3, H2SO4, and my personal favorite, perchloric acid, HClO4. Because when I was 16 and I was looking at the strong acids, that was the one that didn't make sense to me. It's like, ClO4? What's that? So I always like perchloric acid. So strong acids are going to have Ks that are in the order of 10 to the 3, 10 to the 4, 10 to the 5, right? Really big K values. If you have weak acids, you're going to see Kas that are more in the ranges of like 10 to the minus 5, 10 to the minus 2, 10 to the minus 6. So looking at that Ka gives you an idea of your acid strength. Now, of course, we can also write a base equilibrium, because if I've got an aqueous base, it's dissolved in water, so it can exchange protons with the water. Again, because water can act both as an acid and as a base. So we can write the Kb expression for our base, where we have water reacting with the base. So water is the acid. It gives up the proton to the base to become OH minus. The base accepts the proton to become the conjugate acid. And so our Kb, again, BH plus times BOH minus over concentration of B. When we think about strong bases, the standard example for a strong base would be a metal hydroxide. some potassium hydroxide, sodium hydroxide, calcium hydroxide. And these are what we have in terms of our strong bases. So we talked about water as a base, and we've talked about water as an acid. Well, if we have pure water, it can act as both simultaneously. We can have a water as an acid and a water as a base, and this is pretty rare to have happen. So what we have, it's called the autoionization. And so what we have is one water is going to be an acid, one water is going to be a base. So the acid accepts the proton to become H3O+, and the base loses it to become OH-. And this is pretty important for our acid-base chemistry. Again, this is just pure water with nothing else in it is still going to have some H+ and some OH-. Now, we can also write an equilibrium constant expression for this case. What would that be? What would my K be? Well, my products, right, are H3O+ and OH-. So I'd have concentration H3O+ times concentration of O-. But what about my reactants? Right? They're both liquids. And so are they going to be in my equilibrium? Nope. How convenient. So this is called Kw, which is the water autoionization or autodissociation constant of water, which is just the product of hydronium ion concentration times OH- concentration. But this is a very small number at room temperature. 1 times 10 to the minus 14 is Kw at 25 degrees C. It's still an equilibrium expression, so if I change the temperature, what will happen? What happens to an equilibrium constant value when we change the temperature? It changes, right? It's only constant for a specific temperature. So we have to define that temperature. And the standard one for Kw is 25 degrees C. It's 1 times 10 to the minus 14. Not a very big number. So we can use this, though, to figure out the H3O+ concentration in pure water. Because for this equation here, and again, this is just for pure water, right? I've got nothing else here. What do I know for these two concentrations? They're the same. Because every time one water gives up a proton, another one has to accept it. So we know these two are the same. So how am I going to find their concentrations based on this right here? Square root, right? They're the same concentration. So if we call the concentration of H3O+ X, concentration of OH- is also X. X squared equals 1 times 10 to the minus 14. So concentration H3O+ is 10 to the negative 7. Concentration H3O+ equals concentration OH- equals 1 times 10 to the negative 7. And again, 1 times 10 to the negative 7 is still a really small value for a molarity, but it's something. It is a measurable value. Now, when we talk about H3O+ concentration, right, we talk about the pH of a solution. And why do we talk about pHs of solutions? Well, because saying 1 times 10 to the negative 7 and writing 1 times 10 to the negative 7 takes a lot of writing and it takes a lot of words. And we all like dealing with numbers that are between, 1 and 7 or 8, 1 and 10-ish numbers. And so what it means to have a pH is -1 times the logarithm of the concentration of H+. So it's just a function. I can have a pH. I can have a pOH. I can have, if I have a acid dissociation constant, which is Chandra, I can take a pKa. I could take a p of any number I want. It's just a mathematical function, but it makes it easier to write and to talk about our acid concentrations. So if we have a px scale, again, x can be anything, and we take negative logarithm of that number. And that's how we get to P. So if we have H3O plus, then it becomes a pH scale, right? Because H and H3O plus, H plus and H3O plus can be treated as the same, and they're used in the literature, used interchangeably. And so this will become pH equals negative logarithm of H3O plus concentration. So for example, when we have water at room temperature 25 degrees C, right, like we had back here from the auto dissociation, we have H3O plus equals OH minus equals 1 times 10 to the minus 7 molar. And so what is the pH here? Well, what's the logarithm of 1 times 10 to the minus 7? Negative 7 multiplied by negative 1 gives me 7. Excellent. Boosh, 7. And we all know that the pH scale goes from 0 to 14, right? Close. It is most often from 0 to 14. But you can have values outside of this. If I had a 10 molar HCl solution, that means I have 10 moles of HCl per liter. And if I have 10 moles of HCl per liter, what is my concentration of H3O plus going to be? HCl is a strong acid. So what do strong acids like to do? Give up the proton. And pretty much always, once they're dissolved in water, they will give up all their protons. So if I have 10 moles of HCl and it gives up all its protons, how many moles of protons do I have? 10 moles. So if I have a 10 molar solution of HCl, what's my concentration of H3O plus? 10 molar. And so what's the logarithm of 10? 1. What's negative 1 times 1? Negative 1. So a 10 molar HCl solution will have a pH of negative 1. But we don't often use those in the lab because then that really hurts when you get it on your skin. So you can have negative pHs, you can have positive pHs. Right? If I have a 10 molar sodium hydroxide solution, what would the concentration of OH minus be? 10 molar, and again, sodium hydroxide is a strong base, which means it's functionally will almost 100% dissociate. And so if I have 10 moles of NaOH, that gives me how many moles OH minus? 10. So I have 10 molar OH minus. And if I have 10 molar OH minus in water, and I add it here, what's going to happen to this equilibrium? If I've got water with 1 times 10 to the minus 7, and I dump a bunch of OH minus in, what will happen? It'll shift some, okay? But we have this K constant here, so if I have 10 molar OH minus, my H3O plus would then be 10 to minus 15, and so my pH would be 15. So we can have pH values outside of this 0 to 14 range that we're used to seeing, but most commonly we work with 0 to 14. So again, if I have 1 molar H3O plus, then I will have 10 to minus 14 molar OH minus, because we know the product is 1 times 10 to minus 14. And so what's the logarithm of 1? 0. Negative 1 times 0 is 0. So the pH is 0. If we have 1 molar OH minus, right, my concentration of H3O plus is 1 times 10 to minus 14 molar. And so the logarithm of 1 times 10 to minus 14 is negative 14 times negative 1 gives me 14. So my pH is 14. Now, if I were my dad, then I would be wicked good at taking logarithms, because my dad, when he was in my age in college and graduate school, they all use slide rules to do calculations. And slide rules are based off of logarithms. And so my dad always is very good at calculating pHs of things because he's very good at working with logarithms. And so he always, schools me on acid-base chemistry because he's good at logarithms and I'm not because I'm used to calculators. It is what it is. So this is our pH scale, right? So let's do a chem quiz. Which of the following solutions are going to have the highest pH? 10 to minus 3 molar NaOH, 10 to minus 6 molar HCl, 10 to minus 12 molar HCl, right? What does that mean? I have 10 to minus 3 moles of sodium hydroxide in 1 liter of water, 10 to minus 6 moles of HCl in 1 liter of water, or 10 to minus 12 moles of HCl in 1 liter of water. So which of these is going to have the highest pH? What does it mean to have a high pH? The higher pH you are, oh, it's not on here anymore. The higher pH you are, the more basic it is, right? High pH means low H3O plus concentration. Low pH, you're going to have a high H3O plus concentration. So let's see what we got here. $50 seconds. $30 seconds. Be sure to click in. $2.40. We only had like $2.10 this morning. Guess you're all afternoon people. Me too. 10 seconds. Make sure we click in. What do we have before? 2:44? Any late arrivals? 1? Maybe 2? Gonna get 2:50? No. All right, let's see what we got here. Come on. Display. Ah, we're nice and sort of split here. All right, I'm not seeing it. Oh, man, look how funny this is. See, they clicked in D and E, but those aren't actual answers to the question. Man, that's hilarious. Every time, even though we're almost done with the semester. That is so funny. Okay, so we're not to consensus yet. Let's talk amongst ourselves here. Let's get to a consensus. Let's get it right here. Right? 10 to minus 3 moles of NaOH in 1 liter. 10 to minus 6 moles HCl in 1 liter. 10 to minus 12 moles HCl in 1 liter of water. What do I know about pure water that might be important here? Perhaps somewhere in this region. It's hard to say, really. Let's talk amongst ourselves. Let's really think about this. Let's go. Let's get clicked in so I can do my cool demo. I don't know. I don't do that. I think you only have to be right for the bonus question, but as long as you click in and are here, I think that's all that matters for the attendance points. Okay. See what we got here. Oh! We got almost even here, but I'm going to go ahead and go with A. A base should be the most basic. Now, but let's clarify here. So 10 to minus 3 molar OH minus means H3O plus would be 10 to minus 11 molar, pH is 11. 10 to minus 6 molar HCl in water, my concentration of H3O plus is 10 to minus 6, pH is 6. 10 to minus 12 molar HCl, well, I've only got 10 to minus 12 molar H3O plus, except I'm in water, right? I'm putting 10 to minus 12 moles of HCl into water, which already in and of itself will have 10 to minus 7 molar. So the 10 to minus 12 moles that I get from the HCl is negligible in comparison to what is already present in the water. So I go from having 1 times 10 to minus 7 moles of H3O plus to 1.00001 times 10 to minus 7 molar H3O plus. So my pH is essentially not affected because I've already got so much in there, right? It's like if one person came into this room, I'm not really going to notice the difference because there's 240 of you here. But if there were 4 people here and another person came in, then that would be a significant change, right? We've got 10 to minus 7 moles, so adding 1 times 10 to minus 12 moles is not going to have a noticeable effect. Because, and also at the end of the day, right, you do have a base, and a base should be more basic than an acid, and it is. Science works. Now, let's go to the demo, because I've been droning on and on for most of the class. So what we have here is red cabbage. And Karen is going to chop up the red cabbage. If my guinea pigs were here, they would love this. They love cabbage. I tell you what, they should have come to work with me today. But we're going to take this cabbage, chop it up, and we're going to put it into our blender. Red cabbage and water. Will it blend?
Yes.
Yes. So we're going to make a solution here. Now, the chemical which makes the red cabbage red is what we're trying to isolate. Because this is going to work as an indicator for acidic and basic solutions. So today we're going to learn a cool parlor trick to impress all our friends with our knowledge of chemistry, which we all want to do. Set you up for the weekend. So we're going to blend it here. Oh, that smells great. And then we're going to filter it in the funnel because I don't want all the cabbage pulp in there. I just want to isolate that red color. So we're going to filter that, and it's a good thing that Karen is here because I would make a mess of myself if I was trying to blend and pour red cabbage. I'd get it all over my shirt. Okay, and we get this nice purple liquid. And this is going to work as an indicator for me. Sweet. Ah, cabbage juice. No, I'm not going to drink it. I'm not that crazy. Okay, so we've got here a swath of household products, and we're going to look at their pH, starting with muriatic acid. If you've ever cleaned a pool before, you might have come across muriatic acid, which is the old school name for hydrochloric acid. So this is a strong acid, right? I got my purple stuff here. Turns pink. We can move to vinegar. Vinegar is acetic acid, which is a weak acid. HCl is a strong acid. So I put in with my weaker acid. Not quite as red, right? We move on to aspirin. Aspirin is acidic, which is why some people get stomach aches when they eat aspirin, because aspirin has acidic protons. And we put this in here. And I've got my aspirin, a little more purple than my vinegar. Now, the club soda, which has CO2 dissolved in it, which makes carbonic acid. The reason why we waited to pour it is because if we let it sit here, all the CO2 will bubble out, and we won't have as much carbonic acid. So let's see what we got here. More purple. Now we're moving to vitamin C, which should hopefully which should be more acidic than club soda. There we go. Okay. Then we'll move to salt water. Good old salt water. Well, what do I know about salt water? It should be close to neutral because if I have HCl, the conjugate base is Cl minus. Strong acid, weak conjugate base. Sodium is the conjugate acid of NaOH, which is a strong base, so it should be a weak acid. So iodized salt should be around the same, still purple. Now let's move on to me pouring left-handed, and we're going to our bases, right? Baking soda. Baking soda is a common household product. It's base. Ooh. Pretty sweet color. We get into the blues. Washing soda. Who's ever heard of washing soda before? I haven't. This box might be older than me. Maybe it's borax. Who knows? Apparently, it's a value price too. So I'm told. Oh, washing soda. More basic. Now we're getting into the serious stuff. Ammonia from Albertsons. I don't want to smell that stuff. We go with ammonia, getting more green, and Drano, which is lye. Who knows what lye is? Sodium hydroxide. Anyone seen Fight Club? Yes. With the chemical burn? Yes. Don't get this stuff on your skin. And lye is really basic. Ooh. So, if we look at this, we could take a pH electrode, measure the pHs of all of these solutions, and then we would have a correlation between color and pH, which is how indicator works. Give Karen a hand. She blended this. Saved me from making a mess of myself. Right? So we have this whole swath of colors that comes from having, right, the color in cabbage is sensitive to pH. So let's do another chem quiz. Had fun. Let's get back to science here. Let's do this. OK, so Kw for water, right? We said our equilibrium constant changes with temperature. So if we increase the temperature, our equilibrium constant increases from 1 times 10 to minus 14 to 10 times 10 to minus 14. How is this going to affect the pH of just pure hot water compared to 25 degrees C water? Will the pH still be 7? Will it be greater than 7 or less than 7? Equal to 7, less than 7, greater than 7. How do we calculate our H3O plus concentration from our Kw for pure water? How do we do that? Huh? So what's going to happen when my K changes from 1 times 10 to minus 14 to 10 times 10 to minus 14? Or 1 times 10 to minus 13. It's going to happen to my pH. Same up or down. Different K value. 50 seconds. $40 seconds. Who's blowing up? From K, we want to get our H3O plus concentration. All right, Chandra. Ruh-roh. $15 seconds. Make sure we get clicked in so we get our attendance credit. We'll see. How are we going to do here? Am I better at teaching in the afternoon or the morning? Has that turned yellow yet? Yeah, that'll happen. We're all sorts of distributed. We're sort of leaning towards B. We got our Conan O'Briens over here being real funny for our new show on TBS. But let's see if we can come to a strong consensus here. See if we talk amongst yourselves. What's going to happen? How do we calculate H3O plus concentration from Kw? How do we do that? How do we do that over here? How do we get H3O plus from Kw? And then, how do we get from a concentration to a pH? Negative logarithm of that number. That's what P means. Callum and Declan. Callum and Declan. Declan. They're Scottish names. 40 seconds. Let's get everybody in here. When we get this right, we can talk about titrations. I love titrations. Here we go. 20 seconds. Two, one. All right. How we do here? There we go. All right. I am happy with that. Very good. We got, it's E. Get it? E's not an answer. Man, that's hilarious. Okay. Well, to clear up here, right, our KW is essentially 10 to minus 13. And so our KW, right, H3O plus times OH minus, which in pure water are going to be the same concentration. So square root 10 minus 13 is 10 minus 6.5. So our pH is 6.5, which is less than 7. Solid. Okay, I still have 3 or 4 minutes here, so I want to give you a quick start on titrations. So we're talking about strong acid, strong base titrations. So if I have, again, you would do a titration to figure out the concentration of an acid or base really accurately. So if we have 0.1 molar HCl, what's the pH going to be? pH of 1 molar HCl, 10 to the minus 1, log is negative 1, times negative 1 gives us 1. So we start at 1 and we get this curve. The pH of the strong acid in here depends only on the concentration of that acid. If I had 0.001 molar HCl, it would have a different initial concentration because it would have a different thing. Now when we add base here, right, we have 1 liter at 0.1 molar, which means we have 0.1 total moles of HCl, which would be neutralized with 0.1 moles of our base, OH minus. Now, what's the pH going to be at our equivalence point? It's going to be 7 for strong acid, strong base titrations, because what do we have? If I have NaOH and HCl, I'm making salt water. That one, right? Because HCl gives me H plus and NCl minus. NaOH gives me Na plus and OH minus. If I have 1 mole of H plus and 1 mole of OH minus, they react together to give water, right? So K in this direction is 10 to minus 14. So K in this direction is going to be 10 to the positive 14, which is a huge number. So OH minus and H3O plus, they see each other, bam. They're going to hook up and make water, okay? So what we have is water, Na plus, and Cl minus. We have salt water. Salt water is pH 7. Strong acid, strong base, always going to be pH 7. Then as we add more and more OH minus after the equivalence point, what's going to happen is we get more and more basic because we have no acid left anymore, and we're adding more and more base till eventually we get to the pH here being essentially the upper bound is going to be the pH of the OH minus solution that we started with. This works equally as well for sodium hydroxide with HCl, except this time we start around 13 because we have NaOH to start with. As we add our HCl, it becomes more and more acidic, but our equivalence point still takes 0.1 mole of acid because there's 0.1 mole of base. Our pH is still 7 because we're salt water again, and then it becomes more and more acidic because we get a higher H3O plus concentration. Last thing, the pH scale, right? If we change pH units by 1, we change H3O plus concentration by a factor of 10. So pH 1 has 10 times more H3O plus than pH 2. pH 8 is going to have 10 times less H3O plus than pH 7 because it's a log scale not a linear scale. That's all I got. Thank you. Heinel will be back on Friday.